Day, Friday at 4, themed fun stuff going on. More green beer, more green drinks, all that sort of stuff. Concurrently, there will be a charity event going on in the atrium, I believe, called Soul Hope, which is essentially bring in, SOLE. People, you bring in your old jeans, your old denim, and they get fancifully converted into shoes for people who need shoes. So if you have old denim lying around that you don't wear, bring it in. If you want to help the people collect and do the cutting, which I think we have to do here beforehand. That I don't know.
My Canadian tuxedo.
I don't know why you would like that. You should wear that.
It's really clean.
Yeah.
No, just
generally not stained or otherwise disgusting denim. No. If there are some holes in them, it's fine. If it's an enormous hole, I don't know. You can email Elena Morris if you have any questions. So that's going on in here. Also, I think yesterday or 2 days ago, a competency group survey got sent out for an event that's coming up. So if everybody who hasn't filled it out can do us a favor and fill it out. If you need the link again for some reason, just you ping the water cooler and you can resend it. It's very short, few questions about what you know, what competency groups are involved, that sort of thing. Just want to talk about?
Yeah. So next brown bag, we're going to be having a chopped competition. We still need one more contestant to cook, and then we need 2 more judges. So if you're interested in doing that, reach out to me. If you're not interested in doing that, you should still come because it's going to be really funny and fun. But for today's brown bag, we have a really good one also. We have Peter and Andy talking about functional programming, apparently. And I hear there's supposed to be a pretty good finale to this presentation, so make sure you stick around to the end. All right, you guys can get started.
All right, thank you, Ryan. In the functional programming competency group, we decided that it would be a good idea to come up with a series of brown bags, kind of in a similar vein to Justin V's tour of databases. We're going to take a little bit different tack because there's, frankly, databases are different. So what we're going to do is each session is going to kind of build off the session before to a degree. That doesn't mean if you miss session 1, you can't join the session 3. Right? But what we wanted to do was prepare kind of like a path to how more competent, why we care so much about this, why there's actually a competency around it rather than talking about math crap. And so we're going to start with the Groovy programming language. First, I got 4 questions I really want to ask. We're actually going to count hands, so please try and be honest. How many people studied computer science in school? It doesn't matter if you minored, majored, graduated. How many of you didn't? How about that might actually be easier? 3. Okay, so how many people are here minus 3? How many of you studied formally Turing machines? Like proofs, verification of the algorithms. 9, 10, sorry. Mado, your hand is too little. And then how many of you formally studied the lambda calculus in school? 4, 5, 6. That's actually a different ratio than I thought. And then finally, how many of you have read Fred Brooks's book, The Mythical Man Month? 5. Okay. These will all make sense later. Okay, so those questions are helpful to me, not just to know the audience, but to kind of maybe form in your heads kind of where I'm going to go with this. Andy's up here to help me with some questions, and as the leader of the functional competency group, we're going to talk about some stuff at the end. But without further ado, let's get groovy, baby.
No! Never again. Best introduction.
All right. So I kind of touched on this before, but just to solidify what we're doing here, the series is motivated by improving the practices knowledge base of functional programming. I think it's incumbent on us as a functional programming competency to try and disseminate as much knowledge about this topic as possible, so then we can actually win functional programming work. If we don't have anybody that knows anything, how are we going to get the work? So that's kind of selfish on, I think, our parts a little bit, but it's also important. It helps you become a better programmer. We want to reduce the incidental complexity in large programs. Incidental complexity has a specific meaning. Functional programming has tools to help address that, and we'll talk about what that means later on in this talk and in other talks. We want to demonstrate new and improved programming tools. Now, I say new and improved. Not a lot of functional programming stuff is actually new. It's mostly been rediscovered over the years. Used to be back in like the 50s and 60s, you know, Lisp and Fortran were kind of the two languages you had to use if you're not going to be writing machine code. And a lot of the stuff that the Lisp crowd figured out just wasn't fast enough until recently. We have better hardware, better algorithms that have been developed over time, better understanding of things. And so, you know, you see this resurgence in functional programming where the compiler is doing more and more and more of the work for you. The only problem is that you need to know more to actually get that compiler to do that work. So we want to expose everybody to those concepts and get familiarity out there. And then, you know, it's similar to that vein, understanding the actual origins of these concepts. Java has lambdas. JavaScript does a lot of functional programming stuff. There's functional programming libraries out there for it. There's transpilers that are pure functional, pure script, closure script, you know, Elm, whatever. Swift is obviously derived from ML, which is derived from Lisp, which is the granddaddy of all these functional programming languages. And ML spawned off things like OCaml, Haskell, F#. So, yeah, when you see these languages in production today, it's because of, you know, these concepts that were built years ago. Swift is another tack on that kind of same language. And actually C#. C#'s LINQ system, which I love, I think is great, is directly influenced by Haskell. Directly influenced by it. So we're going to take a walk through some of these. And again, the first one is based on Groovy. And so without further ado, let's talk about what the function is. So a function, you can read this, but basically all we're saying is that we're going to take some inputs, and then we are going to map them to some outputs, and they will always maintain that correspondence. For instance, in the equation f of x equals 2 times x, I don't know why MathML decided to make that x like really nasty, but basically if f of x is always 2 times x, and x is some number, then you could call that function times 2, and just move it around, and it'll never change. In different languages, things are called function kind of willy-nilly sometimes. We want to try in this series and in functional programming in general to get as close to the mathematical ideal of a function as we can. If a function does nothing else other than calculate a value and return that value to the caller, we're happy. If the function does weird stuff like write to a hard disk, or I call it weird, and you'll see why in a bit. Write to a hard disk, or you know, pull a random number out of the air, or to receive input, and it starts to become not a function anymore, and it's harder to reason about. Also, if a function is not totally determined by its inputs, then it also becomes harder to reason about. I'm sure you've seen this in a lot of C++ code, where people like are pulling stuff from you know, methods. What are they called? The fields inside of a class, right? And it's like really hard to determine. I just went through this. Really hard to determine like where this variable is being modified or where it's being set. Well, in a functional programming language that actually is functional all the way through, you can basically track back how that variable was defined, built, and received by your function, and understand its flow a lot better. So, and again, just to reiterate one more time, a function can be thought of as a map, and I capitalized map on purpose, because like the Java map, right? You could replace every function in your program with a hash map, and you take the parameters of the function, that's your key, the value is whatever the calculation was, and you're done. And that actually is the basis for a lot of caching that you can do in functional programming languages that you just couldn't do in a language that has mutation as kind of like the first or major system of operation. And so I want to describe these differences, function versus method versus closure. You've probably heard all of these terms in all sorts of different ways. We're going to define them. A method is not necessarily a function. A method usually is tied to some sort of an object or a class with a type. Usually in object-oriented languages, that method does something to the class, so it mutates some variable in the class. Hopefully that's all it does and doesn't mutate some variable in some other class. C++ does that a lot. But let's make a friend. That's a good idea. The method is just a method. It actually isn't a function. And so we're going to kind of discard it for the purposes of this talk. A closure is a special type of function that closes over its lexical scope. So we have examples in here, but that one we're going to talk about because it's really important to, especially when we start talking about things like that, you can actually use closures to represent objects, and they're kind of like the same thing when you get down to brass tacks. So that means it can capture values in its scope during its creation. So you can actually have like a scope, and I have an example of this, that has some variables, and then you create a function that closes over those variables, brings it into its scope, and you can actually return that closure evaluated to somewhere else, and those variables will continue down the line. You probably see that an awful lot when you're doing things like jQuery programming with AJAX callbacks and crap like that, where you have a variable outside the AJAX call that you're referencing inside of the AJAX call when you're doing stuff like modifying like DOM elements or whatever. You know, that's a closure. You closed over that variable, and you have it now. A function that does not close over its variables, so it is totally defined by the parameters you specify to it. It's called an anonymous function or a lambda, and you'll see the lambda calculus this is exactly it. It only has those. And you can take that little kernel of thing, that anonymous function, and you can build your way all the way up to Haskell or even Java or whatever. So when we always talk about first class function, what do we mean when we actually say functions are first class in a language? So the idea is that functions are also values. You can have a function, you can pass it around as a parameter unevaluated. You can then have other functions that take that function as parameters and do things to data with those functions. And it gives you a kind of polymorphism, right? You can, or I guess composition is probably a better word for that, but you can apply different functions to similar operations and get different output. Change the implementation of like the structure and implementation of what you're trying to do. We have some examples coming up. So here's an example of a closure in Groovy. It's basically really simple. You have so def is kind of overloaded in Groovy, but it means sort of the same thing as Ruby. So we're defining something called f1. It takes an a and a b as arguments, and it itself is what Groovy calls a closure, but technically it's an anonymous function because it's totally defined by its arguments. It doesn't have any other arguments coming in. Then it returns, because returns are implicit in Groovy. The last statement is returned as the function's return value. It actually returns a closure that takes x and y and adds a to x and multiplies that by b plus y. I don't care about order of operations here or whatever. So then we make an f2 that's f1 of 3 and 4. So 3 and 4 are bound to a and b, and we actually get this x and y, and that's what f2 is. Then we give f2 5 and 6, it's equal to 29, and then we could actually call it in a chain like this and get the same output. So that's kind of the idea of a closure. Hopefully it's not too confusing. I know I kind of beat it to death, but it's important. So the idea of referential transparency is another big concept in functional programming, and it's extremely important. Basically the idea that any function, given whatever set of arguments, can just be literally lifted out and replaced by the value that it had returned, and your function or your program will still operate the same had you not done that, right? So it's basically saying I can replace this function call with these arguments with just this value that it returned, whatever that value is. Could be a number, could be another function, could be a collection, whatever. And it won't change the output and meaning the output of the program. So that's important because then you can start reasoning about your program more easily than having to get a certain state set up in just the right way so you can test how it works. I can throw every single natural number at a function and make sure it multiplies it by 2, or sample it at least, and be pretty assured that I'm right. If I have to get it in just the right state and just the right format before I check it, that sucks, and I don't want to do that. So here's an example of referential transparency. Basically, we're defining, in kind of in a weird way, S is the successor function. And then you take an n, and it returns an n plus 1, right? That's all it does. So s of 0 is 3. So I can just replace these two and they're equal. S of s of 0 equals s of s of 0. They're the same thing, right? And in fact, I'm not sure if the JIT will actually tear these apart and just turn them into 3s or not. Maybe at some point it could, the hotspot compiler. But anyway, yeah, it's really simple stuff, but it's important that you follow the rules. We've got to be lawful here. Purity. So this relates to referential transparency pretty tightly. The function's only effect is to return a value solely defined by its parameters. I've said that many times. I'm going to keep saying it. Beat it into the ground. Functional programming prefers purity over mutability. Just rule mechanisms for dealing with side effects. In Groovy, since it's basically Java Junior, you just do the side effect and just deal with it as in your head, right? Like, okay, well, I'm doing this weird thing, but I know it's not going to bother anything, so I don't care. Where you get a language like Haskell, you like literally contain that effect in a what's called a monad, and it holds on to it and it actually poisons the rest of that call chain with the fact that there was an effect that happened, and you have to handle that all the way through. I make it sound hard. It's kind of hard to get at first, but once you get into it, it's actually really nice for managing code that can be pure versus code that cannot be pure. So examples of impurity are logging. You're writing state somewhere to a disk or to a Kibana or whatever. Reading from the keyboard, right? You're literally consuming information that wasn't calculated. The human being is putting it in. Generating a number from dev urandom, right? So you need a random number generator. You're taking entropy from the system that you're operating on, and that's not something that you can purely model, right? So that's important. All those things, when we start talking about Haskell, are going to start getting kind of, a little bit different to deal with. So currying is named after this guy, Haskell Curry. A lot of things have been named after him. He's a logician, actually, and he came up with, alongside a guy named Howard, this correspondence that it becomes important later. But they named this concept after him, and that's that you can curry a function by partially applying arguments to it and getting a new function that has like one of its arguments bound. So that means that at the end of the day, all functions are just functions of one argument, and that you can, even if you have a function of 12 arguments, it's actually a function of one argument applied to another argument that returns another function applied to another argument that returns another function, yada, 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 all the way till the end, and then you've done your computation. All programs can do that. If you look at continuation passing style, for those of you that remember that, that's basically it. You pass a continuation alongside your data that you need the function to operate on, and it can just keep going down the chain. It's kind of the same thing. So that's really all you need to know about kind of like terminology as far as this talk goes, and probably the next two talks. Once we get to Haskell, things get a little more hairy. But are there any questions this far into the talk before I start jumping into other stuff? Nope. Okay. So recursion. Recursion is the basis for how programs perform how functional programs, or functions in general, perform iterative tasks. This second sentence is a little heavy on terminology, but basically there's different types of recursion. We care about what's called mu-recursion, mu-recursive functions. That entire space of all those functions is called R in the literature, and that is equivalent to the set of all problems decidable by a Turing machine. If you want proof of that, there's this thing called the Church Turing thesis that was done by Stephen Kleen. Read that paper. It was written in the 40s, I think. Anyway, recursion permits computation, all computation. So we can do the same thing in Lisp that you can do with assembly, that you can do with Java, whatever. It's just different ways of doing it. So here's factorial. You can see it's recursive, right? It calls itself. And there's a little context here that we're not giving because we're not in programs. We can understand that, all right, well, if you give f a negative number, then it's garbage, and some other stuff that, mathematicians probably don't care necessarily about, that computers would care about, because they don't care, they'll just do it. Fibonacci sequence. So again, recursive function, very simple definition. But you guys have probably implemented these things in programming languages. It's not that easy to say this in something like In Java, this is probably pretty close, but in Java, this is not that close. It's a little more complicated. You have to actually deal with things like memory and, what do you actually want to list out of it or whatever. So anyway, recursion allows you to say the same iterative task that you would do in maybe with a for loop or a while loop or a do loop or whatever. You all know about recursion. I'm not really saying anything new, but it's going to pop up in many different places in many different contexts. So just everything we do has a basis in recursion. It's important to know. Composition. So this is my favorite topic, probably because I get to poke it a little bit here. Functions compose, and they compose in a rigorous way. Any of you who've taken any harder math courses, especially things like higher level calculus, know that you can't just like throw two functions together and be a new one. There's ways that has to happen, and you can see here f composed with g of x is just like calling f on the result of g of x. So you can actually make a new function as long as g returns the type that f accepts, called h, where f is composed with g. They're the same thing. You can carry that around, name it something. It's kind of like Unix pipes. For those of you who like Unix, me, you just start piping stuff together, and you can just start creating these chains of things that happen. And as long as everything talks text, you're happy. One of the all it takes is one of those stupid programs like find, for instance, to dump nothing to the terminal if to run xargs on it or whatever to get what you need. But for the most part, it's just like those Unix pipes. You just take one, plug it into another, and you create this kind of like chain of things that happen. It's really nice. It's easy to reason about. Give them good names and you're set. So we're going to compare this to how you compose objects. I took this from Wikipedia. Duck adapter, turkey adapter. This object composition has been knocked pretty hard. The past, probably, I'd say 15 years, the Gang of Four book is starting to get dated with this. A lot of things like design patterns and stuff like that are just ways of getting around the fact that objects aren't that good at anything other than modeling. They're not that good at actually computing. We can talk about that after the talk for those of you who assuredly disagree with me. But every time I work with a complex object-oriented system, I often feel like this child here, attempting to figure out, well, why can't this adapter be there? And I just get it. Right? Functions, if it produces the type you want, it just works. It's great. You can make mistakes, but it's not. Those are logical errors, not like incidental complexities like why is my language pissing me off. So the next step in the talk is higher order functions. So this requires they're like all dependencies, the things we've been talking about, getting into more and more abstract concepts. Higher order functions. Map. Everybody's heard of MapReduce, right? So this is it. This is map. This is map in Java 1.7, approximately. All we wanted to do was take an array list, SS, we're getting it from somewhere, who cares, and we want to return it. And we don't want to modify SS because that would be bad. We're bad if we go ahead and modify that. So all we want to do is reverse every string in it and then return it. So this, correct me if I'm wrong, this is pretty much what you would do in Java. I don't think there's a different way of doing it without just, Apache IO utils, reverse this stupid thing. So, I'm asking some rhetorical questions here. What could go wrong, right? We're saying a lot of stuff, right? We're instantiating new objects. We have to make a new array list. We have to, we have to tell it what size it is. We have to care about these things. It seems like we're saying a lot, and we're not doing that much. We're reversing all the strings in a list. And what happens if we have to integrate this to another program that maybe takes vector, God forbid, or what if we have to extend this to do something else? So in Groovy, this is map. They call it collect because they're jerks. So this is it. It will collect the function reverse. And I'm cheating a little here. Reverse is defined in the Groovy standard library as reverse string. So maybe be a little more verbose if that didn't happen, but still. Collect is saying a lot of things to us at once. And yes, there's some cognitive overhead there, but this is composable of any function that takes collections, right? When it comes out at the other side, it is a collection. It is not necessarily a list or a set or whatever. We can extend this by composing reverse with other functions inside that collect. The syntax gets a little different, and there's actually an example later. And SS is not modified. We are good citizens to SS, right? The set of strings or list of strings or whatever that we're getting in is not going to be mangled by whatever operation we're performing. So if we wanted to compose it with like to uppercase, right? You could just we have syntax, which uses the right shift operator to compose functions in Groovy, and then you have to bracket them so it knows what order to put them in. But I mean, you get the idea. That's pretty simple. I'm going to collect reverse and upper over whatever's in SS. And then I'm going to sort it, right? So it gets pretty simple. It says, again, we don't have to say a lot. We're getting a lot out of it. To do that in Java 1.7, again, we have to do this. We could have made this probably a little bit tighter, but I don't like this code. Look at all the stuff we're doing. Dot reverse, dot toString, dot uppercase, because the types aren't exactly the same. You can't uppercase a string builder. All that stuff is handled under the covers. There's no need for me to know about this at all. If all I want to do is do this. If I want to speed it up, provide a different implementation somewhere else. But this will also, you see, I have to collection dot sort the other array list, or else I blow away SS, and it's it's in place, so at least we're not adding memory pressure. But is that really worth it? In a little example like that, who cares? But you start getting bigger and bigger and bigger examples of, did I allocate that memory? Is it, well, Java doesn't really have all that kind of complexity, but did this happen? Did that happen? You don't have to worry about it. You try and avoid that by using the same kind of higher order operators to get away from those details. So this is something that uses the Java 1.8 streams library. So this is simpler, right? We have our anonymous function. It has to construct it in a string builder because we don't have any choice. But then, okay, we're getting the string and then we're collecting it to a list. So we're still saying kind of a bit, because when you get out at the other end here, it's still a stream. We have to turn it into a collection somehow. And there's kind of like a jankiness to that. Also collect, something that's important is that it actually mutates does it mutate the stream, or does it mutate the underlying?
I don't remember.
Yeah. Anyway, there's something. This is a thing you need to know. I don't touch these things, but this is something you need to know if you're going to be using this to do important things, and you want your data to be consistent. You need to know that happens. So we have to consume all of the input before we're producing a result. The stream didn't help us here. Filter, so another thing. All I want to do is take all the integers that are even and return them. Again, for loop with an if statement in it. I can just do that. Find all is basically filter. Again, stupid name, but it finds all the s's where s's modulus of 2 is equal to 0. Filter in Java 1.8. There's actually two instances here, and Andy, maybe you can speak to why they're different, or if you remember. I think we wrote this before Christmas break, so. But basically, there's a performance-sensitive version, and then there's like a version that looks nice and is easy to think about. I think it's because of the autoboxing. You're trying to avoid autoboxing. Yeah. So again, these things are.
As performance is concerned, you also shouldn't do it in Groovy either.
Well, you got static compile, and it'll compete.
There's going to be more overhead, I would imagine, in Groovy implementation than the Java 8 string.
Well, so
yes.
It really depends on the implementation of the collection, right? Because Groovy, in order to make that Groovy code parallelizable, and here you could kind of do it too. I could put parmap, and it's just, that's parallel now. Here, you parallel stream, right? But it's, again, like more. Like in Java, you have to start a stream, then call it parallel, then do this. In Groovy, pairmap is map. Like, it's the same thing. And in fact, when you start getting into, it's just a different semantic under the cover. It's got a different name, but it's still this like same operation. And Groovy's not the greatest example. The reason we started with Groovy is because it's easy to like slide into from Java.
Yeah.
You can have a valid.
I call it out because you are using Groovy.
Yep. But once we start getting into things like Haskell, like you can do like Stream Fusion and stuff like that, where like the add operation doesn't even look like, when you look at the assembler, it doesn't even do these things. Like, it knows better how to optimize that. But you're right, Groovy is not the best language if we want to do a shootout. So we have a motivating example. It only took about 35 minutes, so we can play around with it a little bit. So we're going to process Twitter timelines in functional programming languages. We're just going to show you what it looks like. You can take a look at how the code operates. We did bring in some libraries, so I don't want any accusations of cheating. But we tried to keep it as functional as possible, try to kind of show where it was important for us to use functional programming to achieve the goals we wanted to. So throughout the series, we're going to work with streaming Twitter data and demonstrate some ETL workloads. To make it interesting, we'll be processing some well-known Twitter feeds. And we're going to take a stream of tweets and use a Markov chain to make our own tweet bots. So our first one is Trumpet. Because he's just amazing. Like so actually, I'm kind of proud because this Markov chains aren't hard. I'm sure most of you have implemented them. You know, probably can attest to, like, it's not hard to make one. It's just kind of annoying. You gotta keep track of some stuff. But actually, I'm gonna keep the one that it first produced when I started because I was laughing at it. Well, basically, he just came out. The Trump bot said, what did he say?
Where'd it go?
Yeah, where'd it go?
Yeah, different.
Oh, is this the wrong window? No! I hate computers. No, it was perfect. All right, well, we'll run it again, whatever. So, you know, you gotta run it a few times to get something good out of it, because it is just a stupid Markov chain. George Bush, and then he says something. Let's see. Dropping out against Obama in 2008, really gets it. So, like, you know, it'll come up with funny stuff. That was just more of an entertainment value, but let's get into the actual software real quick. He said one really good one when I was first starting it. It said something like, "We're not going to let them take our guns." It was pretty much point on. So let's see. I can't even see what I'm doing. You know, I probably shouldn't have done that before I had the thing loaded. Sorry for the delay.
Just have a bash loop running it while you get back on there.
Yeah. Well, so yeah. So basically, that's it. How many lines of code? I can't even read. 118 lines of code to produce all that. That's not bad. You know, when so basically, this is just a script. It doesn't have like a static void int main or whatever. That doesn't make sense. Static final void, public static final void main string args. Yeah. Anyway, this is just a script, but it's got some functions like get tweets for, and it's an API key and a screen name, and it goes to Twitter and gets the tweets. Uses just this little simple get function. Everybody's got something like that now. It adjusts the text, so we replace some nasty characters that Twitter doesn't deal with for us. You know, to just do some more mapping. We lowercase and trim things, and we replace spaces basically. Here we make the Markov chain. Inject is a function that takes an initial starting object and then goes over the object being a collection of some sort, and goes over every single element of it, and it calls this function that you provide it every single time with an accumulator and some element in that particular collection, and then you do stuff to it, and whatever you add to the accumulator in return goes into the next iteration, right? So it's literally going over. This is actually sometimes called reduce, that the other half of the map reduce chain. And something else that we wanted to bring up that I totally forgot to do earlier is that map and reduce and filter and all these things are this one master function called fold. Fold is going to become really important as we move forward in these talks. Fold itself, I believe, is Turing complete. So just fold, which is basically is just like a more abstract version of map and reduce, can do everything a Turing machine can do just by itself. So just keep that in the back of your mind. You know, we have like one function that like kind of rules them all, and we derive other functions from it, which is nice. Especially as we start getting into types, it helps quite a bit. So anyway, we collect some stuff. I know this probably doesn't make a ton of sense, but I'm basically splitting a word into two. There's just two pairs of words coming in, and it just kind of says, okay, well this word comes after this other word, and then it just keeps going down the list. We actually start analyzing the frequencies of how often words come after each other so that we can actually build the chain. I actually am reading the tweets from a file right here because the Twitter API, not that it's slow or anything, but it only gives you 200 tweets at once. And that 200 also includes like retweets and garbage that I didn't want. So I curated the stream a little bit to get the Trump stream. So I didn't have to keep getting tweets over and over and over again. It wouldn't be that hard to do. Or I can get tweets from API. So here I cheated and got them from a file. But then here's the guts. Here's my chain. I'm going to collect for all the text elements in T. I want to ingest them. I need to find all of them that are not empty. And then I'm going to find, this is an interesting trick you can do because our collections are immutable. I take a collection and its tail. And the tail being the collection without its first element. And I put them next to each other and run through both of them until they both end. I add a terminal element onto the tail so I know when the tweet needs to stop. And then this transpose function basically zips them together. So I'll give you an example. This is a pretty neat little function. So let's say we had A, and then we have 1, 2, 3, and 4, and B. We had A, B, no, that's stupid. we had W, X, Y, Z. And then if I did A transpose B, the result of this is going to be 1 W, 2 X, it just merges them together. It's called zip in other languages. Just takes the two lists and puts them together. And then I can pass that into that one function I was telling you that splits the words back into two pieces and does the analysis. Then I inject the empty map into make Markov, so that's where it builds the Markov chain. So from an empty map, I then get a complete Markov chain. And then I analyze the chain. And then I just randomly pick the first element and go to town on it, and just keeps popping out. Picks a frequency, or picks a probability number, picks the frequency based on, or picks the next element based on the frequency of the next element, or if it's terminal, it ends, and there you have it. That's a trumpet. So this isn't really, like this while loop, Ruby doesn't have a great way of doing this functionally. In other functional programming languages, there'd be a better way to do this. But above that, so we'll not count that, this is pretty functional. I think this is pretty clear to understand. Like if you give it some good names, it becomes easy to really kind of understand. Obviously, things like collect and find all are kind of stupid. This should be replaced with map, filter, map, zip, map, and then map again. So you just keep walking down there, doing the things you need to do in order. And this can get optimized too. Because we know that we're not doing any weird crap outside of these calls, you can actually start streaming, well, to a degree, you can start streaming this stuff, or you can do it in parallel, right? I could absolutely do this find all in parallel on however many cores I need to, and then merge it back in later. If I had 1 million words coming out of this ingest text, then I could parallelize it to like 8 processors and do it, faster than I could in just a serial version. And then, you do the same thing all the way down. So that is Trumpet.
So like comparing your line 98, right? So like if you were to do this, without using functional things, one way of perhaps creating the pairs would be to loop over, save the last one, get the next one. Mm-hmm. But because you're doing it like this and you're taking that offset, now you can run those two things in parallel, like you were saying, correct? So like you can.
Yeah. So you could theoretically. Actually, yeah, so that collect statement you're talking about there, so this is actually inside of collect statement. So basically we're taking all the words that are part of the chain, and yeah, doing that like offset. Yeah, offset move, yeah. And so yes, that's absolutely parallelizable. You don't have to, it's doing all that pointer math and all that crap for you under the covers, right? Like indexing into different collections or whatever. At the same time as you're confident that you're not doing something wacky to the collection in order to get your output. And yes, you can parallelize that. As long as this is complete, you can start doing, well, actually this doesn't even have to be complete. As soon as it has information ready, collect can begin, right? And it can do that as fast as it can receive information. So that gets into kind of like that functional reactive stuff a little bit, where, right, you could have functions responding to streams of events that are happening that are not necessarily done, right? You don't have to wait for the execution to complete to start parallelizing the work. And that gives us better, by limiting what we can do, not changing weird values wherever, we can then reason better about the program's operation. Any other questions? Comments, concerns? Else to the other?
I think one thing that might be worth bringing up, and stop me if you touch on this, I just drifted, is that we're separating the description of the program, like what we want to do, from the execution. So
yeah.
Parallel distinction. Right here, we're just saying I want to collect some things, find some things, collect some more things, fold, etc. It's a description of a program. The implementation is not our concern, and that gives the compiler and extremely smart compiler engineers the opportunity to do a better job of it than we can.
Yep.
And
so
also use different versions in different situations based on what we need.
Yep.
I'm really interested later on looking at how to use this to do concurrency and asynchronous operations.
Yep, absolutely. And so actually that kind of reminds me that I neglected to do something, and that's explain why I cared about people who have read the Mythical Manual. In that book, and I suggest everybody who hasn't read it, read it. If you're in software and you don't read that book, you're not doing yourself a favor. There's a guy named Fred Brooks. He was the lead program manager for the OS360 operating system for IBM in the 60s. Massive project, probably the biggest software project ever undertaken at that point. And it was a massive cluster. It was a problem from day one to day like 1300 or however long it took for them to finish it. And he said, why? Why was it so bad? Why do these projects suck so bad? So he actually kind of did a post-mortem and wrote a book. And some of the stuff isn't relevant, like you need a secretary with a telephone book. Like that doesn't matter anymore. But well, it actually is in there as advice. But I mean, that was written in the 60s. But he had this great, I don't want to summarize it, but he had this great understanding of incidental versus essential complexity in software development. And this happens in probably any engineering field, but I think it happens to us worse simply because software is so young. We don't have great ways of formally specifying things that people can really grasp on and understand. So the incidental complexity is like, let's talk about essential complexity first. Essential complexity is the stupid problem. That's why we're all here, right? We have to solve a problem, get an invoice to a customer, collect stupid farm data and put it into something, collect health insurance forms and submit them to Obamacare. You do all this other stuff. That's the essential complexity. Doesn't exist yet, that's why we're writing software. The incidental complexity is like, I gotta write this program in English, or I have to friggin' bring in this library that doesn't correspond with this other library, so I gotta write an adapter. Like, that's incidental. That's not solving your problem. That's just
the way of you solving your problem.
Exactly. It is a problem incidental to the essential problem, which is getting the thing done. So as we go through this series, and I hope what Joel just said kind of touches on this for a lot of you, is that by describing what we want to do here, and not how we do it necessarily. I mean, there's even higher levels of what we want to do versus how we're doing it that we're going to start touching on when we get to the Scala and Haskell sides of this. Is that we don't have to this. Why do I use C and C++ for a lot of this stuff anymore? Because I don't want to deal with pointers. I don't want to deal with value references mutating. It's hard to understand and all this other stuff. Like, there's a reason why things needed to get simpler, and the simpler you can get it, the better you can understand it, the better you can model your problem domain, and the less incidental complexity you have. That being said, there is incidental complexity under the covers. It's not like collect just came out of the ether. Somebody had to write it, but you're leveraging, I'm using that in the right way, you're leveraging the amount of work that somebody did to write a good compiler and a good language. And I'm not calling Groovy a great language, but it's a pretty decent language. It's got its pitfalls, but people have been thinking about these kind of methods for years, eons, in computer terms. We're really good at coming up with ways of making them fast, or thinking about them, parallelizing them, making them safe, making the programs that run them correct, which is another thing we'll be talking on way down the road, where you can verify correctness. But yeah, if you can get away from like, I'm modifying a pointer so that I can look up an index in a table so that I can get this data so I can then do this calculation and present it to the customer, the further away you can get from that kind of like machine stuff, the better you are at reasoning about the like higher level of the program, and the less errors you will have in the program in total.
Yeah, the more brain power you can spend on the essential complexity, kind of focusing where you should be focusing.
Right. Yep, and the less time, right? The less time you have to write, trying to mangle version 4 of this library into version 6 of that one when there's an exclusion on this. Oh, that sucks. If you can get down like as close to functions as possible, then it becomes easier. So that was one key takeaway that I almost forgot to mention. Thank you, Joel. Anything else? Got about 10 minutes. Or I can give you 10 minutes back. You want to see another trumpet? All right, let's see what he says. There was a part of me that wanted to make an actual Twitter bot, and then I realized he sues people.
He says he sues people, he threatens to sue people, and never does.
Yeah.
I still don't want that. You ever talk to a lawyer? They are not cheap to even talk to.
I'll pay your legal fees, Peter.
So see, we found a weird case here. Because we never. Street is a weird word for trumpet. It like keeps persisting on the chain. I actually terminated after like 45 words.
You can actually sing. Let's be honest.
Chairman of real Donald Trump. I wonder who. I'm actually kind of curious.
We're doing it. It's on the internet, you gotta be safe for work.
Yeah, we're doing it live.
Just in case.
No. Trump.
Twitter.
Association endorses Donald Trump. No, we retweet to voters unlike GOP. Anyway, I mean, a lot of the stuff it says makes sense. Some of it's nonsense. It's just a fun little program to make. I know that some other folks are working on different celebrities to make fun of. So Trump is a celebrity, isn't it funny? If you and again, it's actually something I really want to mention. The reason we picked Groovy for this is because it is very easy to slide into from Java. You literally, I think like 90-something%, like upper 90s of all valid Java programs are valid Groovy programs. So you can just start using Groovy. And in fact, if you use Gradle, you're using Groovy. If you use Spock, you're using Groovy. Rails is another project I don't think we use too much here, but that's also Groovy. If you want any help in Groovy, I've been doing it for years. I actually have a couple of commits into the core library. Can help anybody out with it, get started, and you can take baby steps, right? I write a little bit of Java, but now I'm going to use a each instead of for each or whatever, right? And you just start stepping your way into it, and you start getting into more and more functional things. It's a journey, not like an immediate like, oh, I'm a functional programmer now.
Start with your tests.
Yeah, start with your tests.
You can convince clients to write the tests in the language other than Java, use Spock, and
yep, that worked.
Even if they don't want to write the main app in something other than Java.
Yeah, so that's a good way to start.
Is there a property check library for Groovy?
You use Javas.
Yeah, probably Java.
Groovy does some interesting stuff. It's encapsulation. So if you have a private, if you want to get a little tricky, Groovy will ignore things like private, and we'll just go in and take that field right out. It also does not. What else doesn't it do? Anyway, that's funny. If you're like stuck somewhere and you really need access to a field inside, instead of using reflection, just use Groovy. But yeah, so the next one is going to be about Clojure. So it's another JVM language, but we're also going to be talking about Clojure script because I think it's important to have that kind of same language, both sides of the fence kind of deal. And also there's some interesting functions and features in Clojure that you just aren't going to get in Groovy or any other language that's not a Lisp. But and the one after that is Scala, and after that is Haskell, and then after that we're going to go, as Joel put it, full astronaut, and we're going to start talking about things like dependent types, proof systems, stuff that we'll probably never use here, but I think is good for everybody to know exists. Just the state of the art, or it's actually a lot of that stuff isn't state of the art. It's just hard, and it takes years to get good at. So we're just going to do an introduction. I don't think any of us are any good at proof systems. So also category theory. So if you guys are actually interested in like wants all this monad nerd crap about, we can actually go through it and talk about it, kind of explain it, why it exists, what it meant to add that to a programming language, things like that. So anyway, I think I'm done. Did you want to say anything about the?
Sure. Yeah. I mean, we got a little time for more questions if you have any. But if there's anything, we have a roundtable every other Tuesday. We just had it. Well, it'll be this coming Tuesday will be our next one. So if you have any questions, or you're like, okay, that seems interesting, but I have this problem, and I don't really think it fits in functional, bring that to us, and we'll play with it and maybe whiteboard it with you and see if we can kind of work with you to find a way that and maybe you're not going to use it in your application. Maybe it's just more of a, I'm not sure how this would work. I mean, that's fine too. I was talking with one of the client devs last week, and he was reviewing a PR and said, oh, you're using a mutable variable here. Why did you choose to do that? And he went through and he was trying to get a hold of me to our ammo, but I was busy doing something else. So he went off and figured out how to do it using a fold, reduce that Peter talked about earlier. And he was chatting with the other person on the PR. And to me, the reason why he did that, he said at the end when he commented on the PR, just to see if I could do this, I went and did this, and I learned a lot about how to use fold and reduce, and now he's not, he'd be more comfortable picking up in the future. And I said, that right there, that's why you do it. I mean, you just the more tools you have in your toolbox, the better, all around it is.
And it's really valuable to reach one step past the level you think you'll ever use, because if you dabble installer for a while and play with the crazy stuff in there, you can bring the ideas you learned back into Java. Maybe you can't apply all of them, but a lot of them will help influence, like, maybe I do really want value immutability and things like that. And similarly, if you take the next step into Haskell, you then bring concepts from that back into Scala. So it's worth going one step further than you think you are ever going to bother to, because you'll find things that you can bring back to your day-to-day life.
Yep. One thing that I think keeps recurring is that people have already solved all the problems we're solving, aside for like the essential part, right? How to collect over a list, how to get this data into that data, all this other stuff. There's like a million ways to do it. Functional programming has been doing it for a long time. There's actually mathematical bases for all of it. So as we start getting down the path, that like we can actually start showing you that there's an actual mathematical basis for this, rather than like, well, I just threw a couple objects together and this is kind of like what it looks like, and then you start having trouble down the road because, well, they're objects, they're not actual like math. There's not an algebra behind them and things like that. So as we start going forward, those are the kind of things to look forward to. So I think we're done. So thanks for coming. I hope you enjoyed it.